Okay, we're going to start looking at our next main unit, which is our fields unit, which you guys took a little bit last year. You guys took a little bit of gravity, electric, and magnetic fields last year, and this year we'll really expand on a few things. And we'll start with the gravity just like we did last year because it's the one that you guys have the most background with. And it's kind of hard to look at gravity and gravitational fields without going back to some astronomy stuff that you guys actually took in grade 9. Because a lot of the stuff actually came from that type of astronomy and that type of stuff. So just a quick recap of some of the ideas you guys had in grade 9 when you guys took some basic astronomy in grade 9. We started with the geocentric model of the universe way back when, and you guys had looked at Aristotle's theory, where there was like the four-element theory, the earth, wind, fire, and there's the ether going all the way around, and the idea that the earth was the center of the entire universe and everything else was around it. That was expanded out to more of a fancy type model, which looks something like this, which was really developed by a number of people. But once again, we still have the Earth in the middle, and you have all these different rings going out, and you can actually probably recognize some of the names. There's what looks like Luna, which of course is the moon. You got Mercury, you got Venus, there's the Sun, Mars. So these are all the fancy schmancy old names for the planets as they moved out. And if you remember from way back when in grade 9, the planets were held in place on magical crystal spheres. They're crystals, so you could actually see through them. And each sphere actually had one of the main planetary structures on them. And if you look on the outside here, there's actually angels and stuff like that. And up here, that's not Santa Claus. That's actually supposed to be like God. And over here is actually supposed to be Jesus on a cross. So this is a very Christian type of viewpoint. But of course, the idea was you go farther away from the earth, you go far enough away, and you get to the heavens, that type of stuff. So another model of that type of thing looks something like this, where you had the earth in the middle, you got those crystal spheres. Each of the crystal spheres had a planet or the moon or the sun on it, and then one of the ideas was the very outer sphere was actually black, and that's why at nighttime you see black. And then the stars were actually, one of the theories was that the stars were actually holes in the black sphere, and then past that black sphere was heavens or gods, and then the stars were actually little tiny holes in the black spheres, and the light from the heavens was actually shining through. So again, this is some grade 9 type stuff that you guys did a few years ago. Then we also had some other stuff kick in. We've got when they started noticing some of the planets moving, they seem to wiggle back and forth and stuff like that. That was retrograde motion from grade 9. And they had what are called epicycles. So instead of planets actually moving just in a circular orbit around the Earth, for example, Jupiter would move around a smaller circle, and this little tiny smaller circle would actually then travel around the bigger orbit circle, which caused it to have sort of like this loop type path. Now, it was retrograde motion, and Ptolemy tried to explain using epicycles. So this is something else you guys looked at. Now, eventually, of course, this evolved into the heliocentric model, which is the more of a current model, where the sun is in the middle, and of course, the Earth goes around the sun. And Copernicus was a really big guy for this. He's the main guy who actually switched this around 400 years ago to switch the two things around. And as soon as he did that, things worked a lot better because they had a lot of trouble making predictions of where things were supposed to go back in the olden days using the geocentric model, because obviously it's wrong. So the predictions were off, timings were off. It was just really complicated trying to explain everything. So when Copernicus switched the two, things became a lot easier. And of course, we have this type of general structure now with the sun in the middle, planets going around, almost like a big flat disk. It's called the solar plane. And of course, things all go around the sun, and we are held in place by gravity. Of course, the idea of gravity didn't really exist in the full sense that we know of now. And back then, we needed those crystal spheres to keep the things up in space, to keep them from falling into the Earth. So of course, once the crystal sphere idea was needed, you had to have something else holding things in place. And that's where gravity really kicks in. So of course, there's a few people and made ideas that kicked in. Newton, of course, is really important for this. His idea and development of the theory of gravity was really important. Galileo and his telescope was really important. I mean, Galileo looked at the moon, he looked at planets, he looked at things orbiting Jupiter. And of course, his idea was, if moons could orbit Jupiter, if Jupiter was an object that had things going around it, not everything had to go around the Earth. So if the moons of Jupiter didn't have to go around the Earth, why did anything have to go around the Earth? So that was another little theory of why, the Earth didn't have to be the middle of every orbit in existence. And of course, he got into a lot of trouble for these ideas, but it eventually came out better. Of course, changing the orbits from circular orbits to ellipses was also really important. This is where Kepler kicks in. We've got Newton and his gravity, we've got Galileo and his telescope to make observations, and Kepler kicks in with his math. And Kepler came up with his 3 laws of planetary motion, which we'll look at a little bit later on. But just changing the planets from circles to ellipses made things work so much better. Predictions of where things should be, when they should show up, when they should come around. Everything just worked so much better when Kepler's laws kicked in. And the great part is they were so mathematical, it was fantastic. It was really hard to disprove or argue the math that works so incredibly well. And of course, also in the late 1500s, there was a guy named Tycho Brahe, who was an astronomer, watched a comet go through the solar system. And as the comet went through the solar system, if the idea of the crystal spheres was still in place, of course, the comet should either smash the crystal spheres or it should get smashed when it hits one of the crystal spheres, but none of that happened. So once again, it was evidence that there's no such thing as crystal spheres in space holding things in place, and it sort of evolved and was all part of the whole evolution of the idea of how things actually work, an idea for gravity. Now, of course, another really important person with this is actually Robert Hooke, the same guy who did the spring stuff that you guys worked on, because Robert Hooke actually had a theory of how planets could be in orbit. It's sort of like a gravitational theory. He thought gravity sort of acted like a spring, like an invisible spring, not like it was an actual spring, but same idea. Just imagine taking a spring and hanging a heavy mass on it and then twirling it around in a circle, and the spring will actually hold the mass in place in the circular orbit, so to speak. And that was sort of his idea. That's sort of maybe how the mechanics behind gravity works, is it's sort of on the same idea, same premise as the spring idea, where you can't see it, it's not a physical spring, but it's just a neat idea of how it worked. And if you're spinning this mass around in spring and you swing around even faster, it will stretch out the spring and it'll go to a farther orbit. And that's what orbiting objects will do. If they go too slow, the spring will pull it in, which is exactly what happens with orbiting objects. So it's a really cool idea of how this type of stuff could actually work. Now, there's stories out there about him and Newton, and apparently they did not get along, and apparently Robert Hooke really hated Newton. And there's actually some stories out there that Newton actually, apparently Robert Hooke actually proposed this idea to Newton. And apparently one of the stories is Newton actually evolved his theory of gravity based on Robert Hooke's work, and then never gave Robert Hooke any credit for any of the ideas or admitted to actually using any Robert Hooke's work. So there's different stories and variations, but it's kind of interesting. And apparently Robert Hooke really, really, really hated Newton and accused him of ruining his life and a whole bunch of other stuff. So very dramatic. But it's kind of neat how this guy who, for the Springs laws and stuff that you guys took can connect to gravity. It's actually a really neat idea. And there's actually a lot of similarities between how a spring would hold a mass in orbit as well as gravity does. So it's kind of cool. Okay, so next what we're going to do is we're actually expand on Kepler's laws a little bit, because it's the great mathematical thing that sort of tied things together. And we'll look at that a little bit more in detail. All right, so here we have Kepler's 3 laws of planetary motion, typical diagram stuff that you'll see for this type of thing. And they're generally pretty straightforward. The last one looks kind of fancy, but it's generally pretty straightforward. The first one of his laws is really simple, that the orbits of planets and objects are ellipses, not circles, which made a big difference between how the planetary models work, going from circles to ellipses. Things just work a lot better. Of course, an ellipse is, you have circles, and circles, of course, have one center, where an ellipse actually has 2 centers. So you've got your basic ellipse type shape, and it'll have not 1, but 2 centers, which means instead of just having 1 radius, you'll have 2 radii. And if you actually take those 2 radii and add them up, and it doesn't matter where you can go over here, you can go over here, wherever you are, if you add up the 2 radii, they'll always add up to the same amount. So it's a basic geometry type thing. but elliptical shapes work really, really well for the orbits. Okay, so a circle is kind of like a special ellipse, except the two centers are right on top of each other. So if you take these two centers and you'd move them really, really, really close together and then put them on top of each other, you'd actually have a circle. So there's a huge connection between ellipses and circles. Okay, the second law, equal areas and equal times. This is my favorite one in a nerdy kind of way. I just think this is really, really cool. What they figured out is the Earth actually doesn't travel at the same speed. There are certain areas where it's really slow, like out here is where it's going to be moving the slowest, and over here is where it's moving the fastest, because as the Earth goes away from the sun, of course, gravity slows it down, and then as it comes back, it's going to get sped up and whips around, goes slow, and then whips around again. And it can sweep out equal areas and equal times, and that's what this represents. So if it's going over here, it's really, really slow. It's only going to go that little tiny distance in 6 months, and it sort of makes this triangle shape. Over here, it's really, really going, it's a lot faster over here. So in 6 months, it goes a much greater distance. And sort of, well, it's kind of a weird looking triangle type shape, but you take that shape right there, those two areas will have the same area, which is, I think, is really nerdy cool. Even over here, where it would be going like a medium speed, maybe here, something like this. If that is also 6 months, then all three of those would have the same area. So you can do this like you can take a week, you can take a month, you can take whatever time span you want, and it'll sweep out relatively equal areas and equal times, which is very nerdy cool, according to myself. So that's really cool. And if you take calculus and integration and that type of stuff, it's really neat how that type of thing works. Okay, the last one looks really, really, really fancy schmancy, but it's not. If we sort of break it down, and this is sort of like where the calculation actually kicked in, and we sort of, I'm going to summarize this and sort of tone it down a little bit. Basically, if you take the radius of an orbit, the average radius for an orbit, and you cube it, and you divide it by the period squared, and this has to be in kilometers, and this is in years. If you divide those two for pretty much any orbiting object, you will get about 3.34 times 10 to the 24. So this is where the great calculation type stuff kicks in, where you could actually calculate the period for an orbit, the radius for an orbit, because they actually calculated a constant ratio type thing, which is just absolutely amazing. So it's really neat. So if you take like the Earth's orbit and put that in here, which is like 150 million kilometers, and you cube that, and you divide it by 1 year squared, which of course is just 1, you will get about 3.34 to the 24. And I know it's like approximately equal to, not exactly equal to, because it's an approximation, but you can use this for any orbiting object that you want. So it's sort of, you can calculate the moon's orbit, the orbit around Jupiter for one of the moons, the orbit of Saturn around the sun. It's really kind of neat how this can actually work. So just with this alone, with Kepler's 3 laws of planetary motion, you can see like the mathematical beauty and the mathematical significance of this. And it's really, really hard to argue the math. You can argue theology and theories and all that kind of stuff, but he had great mathematical proof and ideas. He could back up his stuff. He could make calculations. His predictions became unbelievably accurate, or astronomers' predictions became unbelievably accurate using these calculations. It worked really, really, really well. And that's why Kepler's 3 laws really were huge for the evolution of the universe theory, as well as the theory of gravity. So combine this with Newton's idea of gravity, possibly based on Hooke, as well as Galileo's telescope. You put those things together and have made huge steps in the theory of gravity and how space actually works. Now, next what we'll be doing is we'll be looking at Newton, more specifically Newtonian gravity, which is what you guys look into. But this sort of is still a baseline for you guys. A lot of this is actually from the grade 9 science astronomy unit that you guys took, and then we'll be building on this, and it's good to have a little background on this type of stuff.